Hey guys, this video is about a qualitative aspect of equilibrium called Le Chatelier's principle. And Le Chatelier's principle states that when a chemical system at equilibrium is disturbed, the system responds to reduce the effect of the disturbance. And reestablish, can't spell, reestablish the equilibrium. So when a chemical system is at equilibrium and it's disturbed, the system responds to reduce the effect of the disturbance. Another way of saying that is the system responds to counteract the disturbance. So whatever you do to the system in a sense tries to reverse that effect. So let's make that a little more real. Let's take the example of PCl3, phosphorus trichloride gas, reacting with chlorine gas to create phosphorus pentachloride, which is also a gas. Now let's say this system has reached equilibrium and the number of these molecules is not changing anymore because the forward rate is equal to the reverse rate, and the relative numbers of PCl5, Cl2, and PCl3, they're not going to change anymore. Now, let's say, for instance, you take this reaction vessel. It's in a closed vessel. And what you do is you add more chlorine gas to the system. You add new chlorine gas to the system. So if you increase the chlorine gas's concentration, so this concentration just goes up, the system responds to reduce the effect of that disturbance. So if that's the case, you add the chlorine gas, the system shifts to the right to remove the chlorine gas that you have added in a way and to reestablish that equilibrium that had already been established. So to remove the stress, to remove some of that chlorine gas, the PCl5 concentration goes up, the PCl3 concentration will therefore go down, trying to reestablish that ratio. And let's say that Kc was already established at, let's say it's 24. So what that means is the system produces more PCl5, right? Because Kc is PCl5 concentration over PCl3 concentration times the Cl2 concentration. So the system wants to reestablish that ratio of 24. And if you make the denominator larger, then the system shifts to the right to produce more PCl5 to make that number go up, and the PCl3 number goes down to reestablish the ratio of 24. Let's say that was not the disturbance, but let's introduce a different one. If your disturbance were to increase the PCl5 concentration by injecting more PCl5 into the system would shift, the equilibrium would shift, that's right, to the left. Because if you increase the PCl5 concentration to reestablish this ratio of 24, the only way to do so is to shift the equilibrium to the left, reducing the PCl5 and making more PCl3 and Cl2 to reestablish that ratio of 24. Other effects may exist too. Let's say, for example, that this were an endothermic reaction. If it's an endothermic reaction, heat is a reactant. Let's say delta H is a positive 24 kilojoules per mole. If delta H is positive, that means heat is a reactant. So that can also affect the equilibrium. If heat's a reactant, if we heat up the system, so if we heat up this system, we in effect add more of a reactant, shifting the equilibrium to the right. Conversely, if this were an exothermic reaction, and let's say delta H were not positive, but instead negative, then heat would be a product of this reaction. And if we heated this reaction, we would drive the equilibrium and push it to the left. The system responds to counteract what you give it, the stress you give it. So if you add heat to an exothermic reaction, the system shifts to the left. However, we can shift the equilibrium in the other direction for this exothermic reaction by putting this system on ice. Let's say we cool this whole system. We put this cylinder on ice. By cooling the system, if heat is a product, we're removing the heat. The heat flows to the outside, thereby shifting the equilibrium to the right. The system counteracts what you do to it. Another example, what could we do to change this particular equilibrium, is we could, in fact, change the pressure. Now, think about it. We have 1 mole of gas on the, 1 plus 1, 2 moles of gas on the left, and 1 PCl3, 1 mole of gas on the right. If we decrease the volume of this chamber, and we put it into a smaller chamber, we decrease the volume, we in effect increase the internal pressures, we increase the concentrations, and because we have more moles of gas on the left, the system shifts to counteract the stress. Because there are more moles of gas on the left, and there are 2 moles of gas on the left, and only 1 mole of gas on the right, if we decrease the volume, the system equilibrium shifts to, counteract the stress, thereby pushing the equilibrium to the right, toward less moles of gas. If, on the other hand, the opposite thing happened, if we took this system and put it into a much larger container, the system responds to counteract that stress. It would shift the equilibrium to the left, to the larger moles, thereby reestablishing the equilibrium. Interestingly, something that does not have an effect on this system would be the addition of an inert gas. An inert gas, such as xenon or neon or helium to the system, while one could see it increases the pressure of the system, it does not increase the partial pressure of our gases. The volume of the chamber is not changing. So if we add an inert gas, such as xenon or neon, to this system, there is no shift in the equilibrium, because in effect, we're really not changing the concentration. There is no change to the concentrations. Couple more things to consider. The effect of a catalyst. Now, a catalyst, as you learned in our chapter on kinetics, speeds up a chemical reaction. Now, it speeds up a chemical reaction. It gets you to equilibrium, is attained faster. So it gets you to the equilibrium state and more quickly, but it does not change the equilibrium constant. Not change K. So it in effect, if this were our case above, if Kc here is 24 of this reaction, what that does for us is it gets us to this place of equilibrium faster. But it does not actually change that ratio of 24. So we just attain equilibrium faster, but we do not, in effect, actually change K. If you want to learn more about that, that's in Chapter 17. The derivation of that is in your book. And one final thing to consider when we're talking about K's is what's called the Van't Hoff equation. So the Van't Hoff equation is this. Ln of K2 over K1 is equal to minus delta H of this reaction divided by R times 1 over T2 minus 1 over T1. The equilibrium is affected by the temperature. And the equilibrium constant K2 at a new temperature T2 can be calculated if you know the original K1 equilibrium constant and temperature T1. Now, of course, temperatures must be listed in Kelvin. Oops, Kelvin. And R here, because we're talking about energy, is 8.314 joules per mole K. And delta H, while we sometimes can possibly express the delta H, as kilojoules, we definitely want to make sure we're expressing it in joules here so that it cancels appropriately. So you can in effect figure out what the new equilibrium constant will be at a different temperature if you know the one equilibrium constant for the reaction at the original temperature. So that's that. We've discussed Le Chatelier's principle. When a system is at equilibrium and that equilibrium is disturbed, the system responds to counteract the equilibrium, the disturbance, and reestablish the equilibrium value. There are different ways to disturb the equilibrium. You can change the concentration of one of the reactants. You can change the pressure if it's a gas by affecting the volume. Remember that solids and liquids don't appear in the equilibrium expressions, and because of that, and pressure actually really has no effect, very little effect on solids and on liquids. And so pressure can change the equilibrium constant if it is a gaseous system. And temperature can also affect the equilibrium constant. And if a system is exothermic, don't forget that heat is a product. If delta H is negative, then heat is a product. And if delta H is positive, heat is a reactant. And I just go ahead and write it right into the equation. The system responds accordingly. The equilibrium responds to counteract the stress you put it on, whether it's on ice or on if you heat it up. And finally, the Van't Hoff equation shows us how the equilibrium constant K is affected by the temperature.